Hello, everybody. Thank you for accepting my contribution to this very interesting Congress. And well, I will talk about a subject of philosophy of biology, but I hope it will be interesting also for analytical philosophers. And this is the topic of complexity in evolution. So I will start talking about why complexity is interesting, and it's one of the three explananda of biological evolution, and what are the main issues regarding complexity. Then I will briefly explain how adaptationism and neo-Darwinism address the topic of complexity, and why I think its explanation is not very satisfying. I will also briefly introduce some other alternative accounts of evolution and of complexity, non-selective accounts, and I will also explain why I think they are not so satisfactory. And then I will show a proposal of a framework to analyze complexity changes in evolution, which could be used both by adaptationism and non-adaptation, non-selective accounts in order to analyze evolutionary phenomena. So let's start with the definition of complexity. Since the origin of species by Darwin, there are basically three things that we would like to explain about evolution. First is why the species seem so well adapted to their environment. The second is why there are so many different types of organisms, why life is so there is such a variety of life. And last but not least, why life seems to progress. In the history of life, organisms seems to become more and more complex. And the first and the second point are well explained by selection. So there is quite an agreement about the fact that selection explains adaptation and also explain why life is so different. The third point, complexity, is a bit more of an issue as per today. So about complexity, I think includes three different issues. First, what is complexity? What is the definition of complexity? How can we measure complexity? Why do we consider that one organism is more complex than another? Or why we consider that an organ is more complex than another? A second issue is regarding the trend. Does complexity really increase in the history of life, and in what sense? Say that today life is more complex than, say, 100 millions of years ago. And also, a very important issue is the source of complexity. Is natural selection real a necessary and sufficient condition for complex traits to appear in organisms? So let's see how Darwin and neo-Darwinism answer those questions. So of course, Darwin believed that complexity that he defined as progress in organization was a general trend in the history of life, at least at the beginning of his consideration. At the end of his life, it kind of changed his mind, but at the beginning he believed that, and he was not alone in thinking this, because Lamarck, Hobbes, Spencer, many others believe the same, that life goes toward more and more complex organisms. And he also believed that selection was the main cause of this trend. So that selection is necessary and sufficient to explain all complex traits in organisms. Of course, this claim is increasingly challenged in the last decades, and there are several alternative theories trying to explain why complex traits appear. We will go briefly through some of them later. And what happened to Darwin's answer today? Well, the modern synthesis, which is like the merging of Darwinism and Mendelianism, try to formalize all those ideas through some simplification. First, it reduced complexity to a scalar value. Usually, they pick a trait of an organism, let's say the length of a leg, for example, and then they consider how does this trait contribute to the fitness of the individual. Then they consider that this fitness should be maximized. They write an equation, they maximize the equation, and they find out the perfect length of the leg, for example. And this is how they consider that traits appear, evolve, and this is a kind of definition of complexity for them. Of course, there are, I think, limitation and strong limitation to this view. First, adaptation consider the environment like something given. So it's there is a world out there, and organisms just are thrown into this world, and they have to adapt to the world. While we know, for example, that a niche is a sum of organism and environment, and they co-evolve together. And the other side is that adaptation considers phenotypes just like a sum function. So there is an objective environment, and in providing this environment, you need some kind of function, and selection will provide the organism with those functions through a fitness optimization process. And of course, this is a very simplified view of evolution, because it says that complexity springs from the need of function to cope with an external environment. So the phenotype is just an anthology of past environment, of past functional requirements. It's something like saying that selection is like a deus ex machina. Okay, it's a kind of religious attitude, and it's easy to see this if we compare some passage from the Bible, for example, to some passages from evolutionary biologists who believe in adaptationism. No? They say selection is always there, sees everything, acts always, and creates complexity. In the last decade, where there are many different non-selective proposals to explain evolution, the appearance of new traits, and complexity. It's impossible to go through all those proposals. Usually they are defined under the umbrella concept of pluralism, which is the idea that evolution is caused together with natural selection by other laws and as well as historical contingencies. The main differences between adaptationism and those other proposals is that they are usually internalist, meaning that they don't consider the organism just passive and molded by the environment, and in some kind they are structuralist. They believe that structure, the trait, comes before function. So selection actually selects the best version of an organism, but does not create the organism, the structure of the organism. And we could classify those proposals in many ways. I classify them, just my way of doing it, by the source, or by where they consider that the source of complexity, of new complex traits lies. So in the genotype, phenotype, in the developmental system, or in the organism as a whole, as a complex system. We go briefly through some of them. For example, if we consider the genotype as a source of new traits, the neutral genetic networks proposal by Andreas Wagner claims that it's possible to have mutation and recombination at genetic level without an immediate phenotypic effect, so that the phenotype is not affected by those mutation and recombination. But those changes can, little by little, accumulate, and at the end they can give rise to a new function or a new trait without losing the original function of the phenotype. So the new organism, after many generations, can have a new function that appears suddenly, not little by little, like adaptationism claims. Regarding the phenotype as a source of novelties, there are also neo-Lamarckian theories saying that sometimes environmental stress can cause mutation, and contrary to what adaptationists claim, those mutations are not random. They are targeted to specific genes, and to those genes whose mutation are more probable to provide a new function able to cope with the initial environmental stress. Then we have proposals that identify the developmental system as the source of novelty. We all know that to pass from the genotype to the phenotype, there is a long way, and so it's not enough to have a genetic encoding of a dinosaurus, for example, that we can recreate a dinosaurus. We also need a lot of information about the developmental system of dinosaurs that we do not have. So the idea is that the developmental system poses great constraints to the generation of new traits, and that the modification of a phenotype is not of little by little changes, but it's a process of a sum of an on-off situation. So we have many points in which we have to decide where we go, and so at the end the phenotype is not a little bit different than the original one, but quite a bit different. And then the last big group of proposals consider that organisms are, of course, physical entities, and they must comply with physical, chemical law and complex systems law, like self-organization systems. And it's interesting to notice that if, for example, if we map metabolic rate of organisms with body mass in different species, we get the same exponent. And this is a logarithmic scale, and they're all mapped in the same law. This is not the result of action. This is clearly the result of some physical mechanism that maybe we do not understand perfectly, but it's clearly not selection. So those are few of the many non-selective proposals to explain the evolution of complexity. But how do we have seen that adaptationism reduce the individual, the organism, complexity to one value, fitness, or to the value of some phenotypic trait. Oh. On the other hand, there are many proposals to define complexity in a more complete way. And I have classified them in three big groups. There are many more than that, but just to give an idea. Usually, they define the complexity of an organism based on how difficult it is to, for example, build the entity, which is the typical developmental question, or how difficult it is to describe the entity, which is typical structuralist question, or how difficult it is to describe the relationship between the entity and the word, like an adaptationist question. All those proposals are very complex in themselves, and it's almost impossible to apply them to real organisms. Sometimes authors try to apply them to genetic encoding, but again, real complexity is not at the genetic level, it's at the phenotypic level, because genetic level is just a string of information. But how we transform this information into an organism is not so linear, it's not so easy. And so we arrive at the last issue about complexity, which is, does biological complexity increase in the history of life or not? Well, it's easy to answer the question, but it's not easy to make the question in the first place, because what does it mean that complexity increases? That it is a general trend in the majority of species, and a few lineage become more and more complex, while others remain equal. For example, there is a species of salamander of the family Plethodontidae that persists with little change since over 50 million of years, while the environment did change. So it's clear that selection is not a main driver of evolution in this case. And of course, we can also have cases, well, half of the lineage show increasing complexity, the other half decreasing complexity. So it's not easy to define this question, and it's not easy to answer the question. So we arrive at the proposal that we make regarding complexity. We have seen that there is no agreement, biologists and philosophers of biology, around a definition of complexity, because for adaptationism, it's fitness and it's a too simple a definition. Other proposals are maybe too complex to be applicable. There is no agreement of a source of biological complexity. For adaptationism, in selection, but we've seen it's like a deus ex machina. It's an explanation that doesn't explain much. And other proposals are very, very different among them. There is a huge quantity of proposals, and many of them are still discussed. And also, there is no agreement about the existence or not of a trend in complexity in the history of life. So, to overcome those problems, what we propose is a bidimensional function space. and that shifts the focus from complexity to complexity changes, and classifies evolutionary phenomena as changes in morphology and in function of an organism. So we do not define complexity, we just track complexity changes, interpreted as changes in form and function. There is no need to link the definition to a source of complexity. Selection of others is agnostic in this sense. And it's completely irrelevant to know if there is or not a trend toward more higher complexity, let's say. So our idea is to start from analyzing different evolutionary phenomena, any evolutionary phenomena. We have a typical textbook case of Bistum betularia, the butterfly whose wings changed color during the Industrial Revolution in England because the color of a tree changed color. So for the birds, it was easier to eat the white butterflies instead of the black one. There is another textbook case of Darwin finches, those finches that change the conformation of their beaks in different islands. And we have a great evolutionary change, which is the appearance of flight in dinosaurs. So if we analyze, for example, those three cases, we can see that in each of them, form and function change in different ways. In the Bistum betularia, the form didn't really change. It was already there, the wings. And the function was the same before and after the mimicry. In the case of finches, well, the form changed a little bit. We had a new version of the same form, the beak. And the function was improved because with a new beak, we could access to new kind of foods. And for flight, we had, of course, new forms, several new traits, and a completely new function. So regarding function, we have seen the three, for example, the three options that we have before and after an evolutionary change. We do the same in the same way, so the function doesn't change. We do the same in a new way, so in an improved way, or we do something totally new. Regarding form, again, the trait can remain unaffected, like in the case of Bistum betularia, or we can have a change in an existing trait, qualitative, quantitative, relational. We can have a new trait or a new arrangement of traits, which we call a module, or we can have a new arrangement of modules, we call a body plan. We have some examples here. The first one is the loss of vertical symmetry of ears in some species of owls in order to be able to detect the height of a sound. So it's not like, for example, we can detect the direction, the horizontal direction of a sound because we have 2 ears, but not the height of a sound, while this kind of species of owls are able to do that. And then we have potential qualitative or quantitative changes. Then we can have a novelty like fevers. Fevers was a great novelty in the history of life, and they appeared because of thermoregulation ability of fevers, not really for flight. And we can have a new module, like the pentadactyl limb structure in vertebrates is a module that appears and is shared by all vertebrates now in the world. And we can have a new body plan, like the turtle carapace is really is made through the fusion of bones and skin in the turtle. So it's a completely new body plan, which is typical of the Chelonian family. So finally, we can map all those changes in a bidimensional space where we have function and we have form. And we can have, for example, the case of Bistum betularia, where we have the same function and the same trait. So at the end, it's the same organism architecture. And we can hardly talk about evolution here. It's just a change of frequency in a population. And here, for example, explanation by selection works very well because we do not have new traits. It's just a selection of existing traits. But then we have a universe of other potential evolutionary phenomena, which fill all this area. So, for example, exaptation are existing traits that suddenly are used for a new function. So it's a typical, again, selective explanation. It's the same trait which is used for something new. We have the turtle carapace or flight. Of course, we have a new body plan and a completely new trait. And we have cases in the middle. For example, we have redundancy for duplication of organs. We have, for example, 2 lungs because breakup of one for the other. So we have just the same or improved function with a new module. but we also have redundancy of new function. For example, we have two eyes. Thanks to our two eyes, we can calculate distances. So we have stereoscopic vision. And this is not just a redundancy like backup, but it's a redundancy which adds a new function. So the idea is to map in this space an evolutionary phenomena before even deciding if it's an improvement or not in complexity, or if it is due to selection or to some of the other non-selective accounts, but just to understand the phenomena, to map it, and then to try to understand which forces contribute to this evolutionary change. So in this sense, it's totally agnostic. It's a framework. It's not a theory or a proposal to explain why complexity arises. It's a tool to start with in order to first do not suppose that selection or other forces are responsible for the change before having any information. And second, to separate function and form without being functionalist or structuralist. We do not say that form is first or function is first. We just know that at the end, something changed, and then we can start analyzing why and how. So the proposal, we think, has advantages. First, it advances the request for an absolute definition of biological complexity. It supplies a way to measure complexity change, separating evolution of form and function. It's agnostic with regards to the causes of change. So it's able to take into account any source of biological variation. And so it's just a flexible classifying tool that can be applicable to any kind of account, adaptationist, selectionist, or not. And so this is it. And thank you very much for your attention.
Thank you very much, Giorgio. Now we are open for questions. David has one question. David, you can.
Yeah. Thanks, Giorgio, for the presentation. Very nice, very enlightening. It's a clarificatory question. How is the debate between punctuated equilibrium and gradualism related to the debate on the explanation of the increasing complexity? I mean, is it possible to observe huge leaks in complexity from one species to its more related ancestor in the taxon, or is gradual in a taxon, for example?
Yes, thanks for the question. Yes, the punctuated equilibrium is one of the first examples that were made by Gould a few decades ago to show that evolution is not always gradual, because the idea is that if we consider the gaps that we find between species in the material that we have, sometimes we don't have all the intermediate species between one and another. The classical idea is that those species, well, the remaining of those species are lost forever because it's difficult to find those remainings. But the idea of Gould is not, is that those species simply do not exist, that the jump was sudden. So this is, again, alternative account to classical adaptationism, which says no, changes are accumulative, sum of little by little improvement. And so as a matter of fact, I think it's a very good example of non-selective accounts of evolution, in which we cannot recur to selection to explain why these new species appeared, because there is no empirical evidence that selection was responsible for the new trait.
Okay.
I don't know if I've answered the question.
Yeah, totally. Thanks.
I also have a question.
Yes, I do have a question. Genetic programming has been a very nice computational environment to test evolutionary theories. Have you tried to experiment and test your ideas in this setting?
Not really, no. Also because, as I was mentioning in the presentation, I think that complexity is more on the phenotypic side, and the genetic side of evolution is, of course, very important. But then between the genetic encoding and the phenotype, there is a huge, a lot of things happen. For example, in the developmental system. And the developmental system is embedded in the environment. So you cannot really, from the genotype, you cannot really decide what the phenotype will be. So the genotype cannot, in my opinion, really tell you if the organism will be more or less successful, and what will the traits of the organism really will be. Of course, it gives a lot of information, but it's not all there. So as a matter of fact, population genetics has a lot of formalization, and it works very well, but it works very well, especially in very simple organisms. I'm sure you all know the experiment by Lenski, which is, I think it's already 25 years or 30 years, but he's making this experiment with Escherichia coli bacteria, with a population of Escherichia coli. And of course, it's bacteria whose life is very short. So 30 years is the equivalent of, 1 million years of evolution in other species. So he has accumulated a huge amount of information to show that selection really works. And of course, it works at the genetic level for such a simple organism, for which the phenotype and the genotype are also almost the same. But to make the same analysis for a complex organ, I think it's difficult, and it's not really feasible.
Very nice, Giorgio. Thanks for that.
Thanks.
I was just wondering, well, I know you have a PhD dissertation on this topic, so you are probably the most well-prepared person to say something about, I mean, in which sense could this view you have just presented help us to improve our understanding of the evolution of the human brain? I'm thinking here, the brain is just one of the most complex thing or object I know of. And it's obviously architecturally complex and functionally complex. And I mean, would you elaborate a little bit on this point?
Yes, thanks for the question. I'm not an expert in evolution of human brain, but I think the brain is a good example of something that selection alone cannot really explain. Maybe it's more a question of complex system laws or expectations. For example, we know that some parts of the brain which allows to work on Wikipedia working are also involved with language. So it's I think it's an interesting area to analyze with non-selective accounts. So the idea would be to identify some evolutionary phenomena affecting the brain and trying to understand really in which sense the structure of the brain and the function performed by the brain have changed. Of course, this is very difficult because the brain, we do not have brains of previous. We have bones, but not the brains of previous. It's true that in the skull, usually you can find some information about the brain and the structure of the brain, but it's of course very poor information. But I think it's a typical area where selectionist accounts simply do not work. I mean, once I remember I read this text when I say, okay, that humans became more and more intelligent because females prefer more intelligent partners, which, I mean, apart from being very racist, because I mean, maybe men also prefer most intelligent female. But how do you measure that? I mean, it's of course, I think it's a typical area where adaptation is little to say, and other non-selective accounts, especially complex system laws, are more involved, or maybe cryptic genetic changes, or linkage between genes that one function suddenly give rise to another one. Also because I think that the brain is a good example of a potential tool that has not been exploited in the first, maybe I think the Homo sapiens is around since 200,000 years. And what happened during the first 190,000 years with all the potentiality of the brain? We were not really used for surviving. So I think the distinction between structure and function is especially relevant here. Thanks for the question.
We also have time for another question from Jefferson Giallo Hufferman. He said, "Thanks, Giorgio. I would like to ask if the time scales could be used by a more adaptationalist account to put all of our examples in the same framework."
Okay, thanks for the question. It's a very good question, because actually the time scale is fundamental, especially for adaptationism, because adaptationism will always tell you, okay, give me enough time and this will happen. Okay, if you say, no, there is a constraint, a genetic constraint or a physical constraint, so that you will never be able to have an organism doing this, and you say, no, not yet, but if you give me enough time, little by little, we'll get there. Selection will find a way to avoid this constraint. So in some sense, in a very long time frame, yes, it could be an interesting variable to add to the model. I still think that there are some phenomena that adaptation cannot explain, even if we wait long time. There are no organisms with wheels, for example, and maybe wheels are a very efficient way to move around. Or we have no birds with separation between the motor of a flight and the wings. The birds use the wings to move and also to sustain themselves, while airplanes have two different elements. Wings just sustain the plane, and the motors move the plane. But we have no organisms doing like airplanes. Maybe airplanes are more efficient than birds in doing this. A selectionist will tell you, no, it's, the best way to do it is like birds do. Because in a very, very long time span, they have tried all the possibilities, and at the end, they've selected this one. So, yes, the question is very good, and it's, of course, it could be. But, well, I will think about it. Thanks, Daniel.
Okay, thank you very much, Giorgio. Thank you all the presenters.